my classes on fundamentals of electrical circuits. We move on to three-phase AC circuits. Okay, and just as AC is easy, three-phase AC is also very easy. It is just that you've got to uh, project a little more or extrapolate a little more about the three-phase when compared to the single-phase. Okay, so we are, as is mentioned here, we are going to move on to the easy problems in three-phase AC. Okay. So just let us look at the first problem. The line A to neutral voltage is 10 angle 15 degrees for a balanced three-phase star connected load with phase sequence ABC. Okay, so the voltage of line B with respect to line C is asked. Okay, and four options are there, and we can see that all the answers have 10 root 3 except one. So definitely B will not be an answer, but still let us see how it is so. Okay, and of course the angles are different. Okay, so just for reference sake, I have given a drawing alongside, and please notice that though it is mentioned that line A has a voltage with respect to neutral as 10 angle 15 degrees, the amplitude is RMS value as was mentioned before, and the angle is with respect to the horizontal. Okay, so and it is positive in nature, which is reflective of the fact that you have an angle in the counterclockwise direction. Okay, unlike in the case of AC angle, unlike in the case of electrical angles or electrical oriented angles, wherein the angle is angle of the power factor angle or whatsoever is with respect with is in the clockwise direction. Okay, so 10 angle 15 should have had a magnitude of 10. Okay, and rather VA should have a magnitude equal to 10, and it should have been 15 degrees in the anti-clockwise direction. But I have drawn it in this manner such that it can be a reference for all the problems. Okay, so now we have VA, and then since the phase sequence is ABC, you go along the clockwise direction because it is an electrical quantity. Okay, so we see that 120 degrees away from VA, we have VB, which is the phase voltage of B phase with respect to neutral. Okay, another 120 degrees again proceeding in the clockwise direction. You encounter voltage VC, which is the phase voltage of C with respect to neutral. Okay, and now what is asked is VBC, which means that, as was mentioned before, B should be more positive than C, or in other words, it is the same as equal to VBN minus VCN. Okay, or in another sense, you have to reflect back, or you have to you have to get the mirror image of VC, and that is what is done here. And you can see that V minus VC is the red line shown here. Okay, so now what is VBC? It is the same as equal to VBN plus minus VC. VBN or VB minus VC. Okay, so now so what does it mean? You have what is called as the total of two values, and they are at 60 degrees with respect to each other because VC is reflected back. Okay, so if the angle between them is equal to 60 degrees, then and they are of equal magnitude, or VB equal to VC in terms of magnitude, then the resultant will be root 3 times. Okay, on the other hand, if the angle between them is equal to 120 degrees, then the resultant will be the same as the components. Okay, so here now 10 root 3 is justified. Now regarding the angle, it is very clear that it should split between the two, or in other words, it should make 30 degrees with respect to each of them. Okay, so obviously we see that VA and the VBC happen to be at 90 degrees with respect to each other, but of course VA is shifted. VA has been placed on the horizontal, or in other words, the entire assembly now has to move in the counterclockwise direction with respect to 15 degrees. Okay, or in other words, 90 minus 15. Okay, or minus 90 plus 15. Okay, because it's moving in the counterclockwise direction. So 10 root 3 angle minus 75 degrees is the answer. Okay, similar problem is what we have in question number 2, which says that suppose IA, IB, and IC are a set of unbalanced phasor currents in a three-phase system. The phase B zero sequence current IB0 or IBO is equal to 0.1 angle 0 degrees per unit. If phase A current IA equal to 1.1 angle 0 degrees per unit, and phase C current IC is equal to 1 angle 120 degrees plus 0.1 or 0.1 angle 0, okay, per unit. Then IB is in phase is what, okay. So there are several aspects with respect to phase with respect to symmetrical components. One is of course the fact that IA0 is the same as equal to IB0, which is the same as equal to 1/3 of IA plus IB plus IC, okay, and that is given as equal to 0.1, okay. So that's point number 1, okay. So it's already given as equal to 0.1, okay. And what all do we know here, okay? So we are just now substituting in this equation. That is, we are saying that we are just outlaying them. We know that IA is given and IB0 is given, so we can substitute IB0 is equal to 0.1, which is already done, and then you can write that A is equal to IA, so 1.1 angle 0, that's also outlaid there, and then we have IC is equal to 1 angle 120 degrees. So 1 angle 120 degrees now has to, and of course 0.1, so that has to be now resolved into two components. So 1 angle cos 120 is also 1 cos 120 and 1 sin 120, and that's split here and written as equal to minus 0.5 plus 0.86. Okay, so that then putting them all together, this equation is now supplemented with or substituted with all the known quantities. So the only unknown quantity now becomes IB, and so IB is solved as equal to 0 minus 0.54 minus j 0.86. So we have worked with rectangular components all through. Why? Because the answers, as we can see, have two components. One is the polar quantity, and other is without the polar quantity. So what do we do? So now we try to write out the same thing, and that is what we have obtained as minus 0.4 minus j 0.86 is as equal to minus 0.5 minus j 0.86, which is equal to again 1 angle. So it has to be 1 angle, both quantities need to be negative, or in other words, it's going to be 1 angle minus 120, and it's also having an additional 0.1 has been taken, so that has been deducted. So that has to be an additional minus 0.1 has been taken into consideration, so that has to be deducted. Okay, so we see that the answer is D, and it's equal to 1 angle minus 120 degrees, as was mentioned before, and with also the additional component of 0.1 or 0.1 angle 0. Okay, so moving on to, so these are just arithmetic arithmetic manipulations that we have done. Okay, so now moving on to the third problem, wherein a three-phase balance. So in all these cases, we have to read a little patiently, but the answers will come very quickly. Okay, so long as we know some of the formulae that we'll be using. Okay, so a three-phase balanced star-connected voltage source with frequency omega radians per second is connected to a star-connected balanced load, which is purely inductive. Okay, so please remember, all the entire load, star connected load, happens to be inductive in nature. Okay, the instantaneous line currents and phase to neutral voltages are denoted by, they are given as IA, IB, IC, and VA, VAN, VBN, and VCN. Okay, the instantaneous values with respect to neutral. Okay, the voltages. Okay, respectively, and their RMS values are denoted by V and I. If okay, R equal to, now R is given as equal to VAN, VBN, VCN multiplied by a matrix, okay, as given by so the VAN, VBN, VCN, which is given as the instantaneous value, is given by is written out as a row vector. Okay, and then we also have a column vector on the other side, IA, IB, and IC. So of course there is compatibility between the matrices, because if you multiply the whole thing, you get a single value, and that is the value of R as is given, which is what is given. Okay, and what is inside the matrix? Let's see. 0, 1 by root 3, minus 1 by 3. That's the minus 1 by root 3. That's the first row. Second row is minus 1 by root 3, 0, and 1 by root 3. And third row is 1 by root 3, okay, and minus 1 by root 3 and 0. Okay, so what do you surmise out of it? You see that the complete the entire diagonal is equal to 0. So its determinant will become 0. Okay, if the determinant will become 0, then if you multiply whatever with the determinant with the matrix with the determinant as equal to 0, then the resultant is going to be 0. Okay, so of course you can multiply and see, but then these ideas of borrowed from mathematics can be utilized in three-phase circuits as well. Okay, moving on to problem 4. A three-phase balanced voltage is applied to the load shown. The phase sequence is R by B. IB, just as we saw earlier. And so what's the ratio of IB? So all these problems are easy so long as you are ready to accept that they are easy. So what is now given is IB. Okay, so again, vector diagrams, if you have a degree, if you have a clear understanding of vector diagrams and how to draw them, you can immediately find out the ratio of IB and IR. Of course, only the magnitude is required. The sense is not taken into consideration, or the sign is not taken into consideration. So let's look at the diagrams to see what is IR. Okay, IR is flowing through a minus J10 ohm capacitor or capacitive reactance as given by J10, and then there's an inductive reactance through which of magnitude equal to J10, again through which the current IY flows, and then they flow together. Okay, of course, when Kirchhoff's current law tells us that if the currents flow together into the junction formed out of the three, then that current flows back as IB. Okay, so but of course IB is shown as flowing inward. Okay, so IB has no impedance; it faces no impedance. Okay, so now what do we have here? So we have, okay, as usual, we know that the supplied voltages VR, Vy, and Vb. Okay, as is given, and the phase sequence, we have followed the phase sequence by putting them accordingly in the vector diagram given alongside. Okay, and now we have what is called as we have we realize that that is VRN divided by minus J10 is going to give you IR. Okay, so that's, so what does it mean by division by 10? Okay, so there's a magnitude. Okay, and that has to be divided by 10. Okay, so that so we are okay with that. Okay, whatever be the magnitude divided by 10. Okay, and then what happens? Minus J10 is on the denominator. Minus J is on the denominator, or in other words, minus 90 degrees also on the denominator, so plus 90 degrees. Okay, so whatever is given as VR, to which you will have a lead angle of 90 degrees. And when you're talking about a lead angle, when you're talking about 90 degrees, it means that you have to go in the counterclockwise direction, and accordingly IR has been shown here. Okay, then moving on to what happens to IY. Okay, that's again VYN divided by J10. Okay, so now we see that we have already placed VR, Vy, and Vb, and now we have an angle of not a lead but lagging, as is always indicative of an inductive, or by division by J quantity. Okay, so when you're dividing by J, it means that there is an angle 90 degrees on the denominator, or a negation of an angle by 90 degrees, or going back. Okay, and that's why we have gone back, and we have shown the current IY. Okay, again we see that now IR and IY happen to be we can just calculate the angles, like for instance from VR 90 degrees, and then there's a 120 degrees with respect to VR and Vy, and then another 90 degrees. So what should be the angle between the two? Okay, so just calculate all the angles. You can see that there's only 60 degrees between them. Okay, if you just simply draw once, it will be very clear to you that there's only 60 degrees between them. Okay, so 60 degrees means again another root IB will be given by root 3 times. Okay, and of course the angle is also shown. Okay, and now what is asked is the magnitude of IB and the ratio of IB. Okay, so IB is root 3 times. Okay, it is 1.73 times of the individual values of IR and I. Okay, so in a simple manner, just by looking at the vector diagram, you can go for AC problems, especially the AC three-phase AC problems. I think the fifth problem is also similar, because we are given voltage V1 as. Okay, so these kinds of problems are repeated, especially because you're supposed to know the vector diagram. Okay, so once you get through the three vector diagrams that are covered here, I think you will be very clear that it's easy to do such problems. Okay, so in the given problem, V1 100 angle 0, V2. Okay, so the same VR by B is now talked in terms of V1, V2, V3. Sometimes they are talked in terms of A, B, C. Okay, so V1 100 angle 0, V2 100 angle minus 120. Okay, so phase sequence is 1, 2, 3, and V3 is equal to 100 angle 120. All are equal, of course, as is obvious, because supply voltage is always considered to be balanced. Okay, the phasor current I in amperes is. Okay, again we see that V1 phases minus J1 impedance, okay, or a capacitive reactance. V2 phases minus J1, and then the totality current, the total of the current flows through the third phase, okay, as I. Okay, of course the direction is opposite. Okay, so that's all that we've got to do. So we see the lesson that we have learned earlier. or the diagram that we have learned can be utilized. Okay, so just a little difference has been brought about here because we have a difference here. Okay, in the sense that it is not VRN, okay, or VYN or V1N, V2N, which is driving the current. It is going to be the voltage between the phases. Okay, so V13 and V23 are going to be the voltages across the two bits of impedances, which is going to drive the current. Okay, so unlike in the early case, that's the only difference here. Okay, so what do we do? So now we have to find out what is called as V13. Okay, so reflect back 3. Okay, because both V23 and V13 require the reflected third phase. So V13 is drawn here. Okay, and so we reflect back V3. So we get minus V3, and then between them you get V13 root 3 times the individual voltages. Okay, okay, and of course 30 degrees with respect to each other. Okay, so similarly V23 can also be obtained because we already have V2 and V3 is reflected back. So between them you get what is called as V23. Okay, so again the magnitude is root 3 times, and the angle is such that they occur between the two voltages. So that is V2 and V minus V3 and V1 and minus V3. Okay, so once that is done, now it's very simple to realize that you have just got to divide by 1, because both the reactances are of magnitude equal to 1. Okay, but of course there is an angle. Okay, like for instance, when you're dividing by the capacitance V13, you are going to have an angle of minus 90 degrees on the denominator, or a positive angle, or in other words a counterclockwise direction for the current. Okay, so we have I1 now as equal to I1 is set at 90 degrees with respect to V13. Okay. On the other hand, when you're looking at V23 and the current driven from the source voltage at 2, you see that there is a lagging current. Why? Because it's an inductor, okay, of 90 degrees. Okay, so just take back the current, and so you see that there is a 90 degrees between them. Or in other words, again you see that you have 60 degrees between them. So now what is the current? You can take you can see that it's going to be root 3 times this. Okay, and thereafter you can also find out the angle. Okay, so the answer is now going to be 173.2, because the division has always been by 1, so we see that the answer is equal to 173.2, and then the angle is minus 60 degrees. You can just draw once, it will be very clear to you. Okay, so problem 6 is repetitive. It is similar to what we have done earlier for the three-phase circuits in question. The ratio of the currents Ig. Okay, Ig is going to be the so Ig is okay. I think it is a mistake. That's IR. IR is to Iy is to Ib is given by. Okay, so IR is going to be IR is going to be facing resistor R1. Iy is going to face resistor R2, and Ib is going to be the totality of these two currents. Okay, so it's very clear that it's that when you are having a sum of two currents, okay, and that too at 60 degrees with respect to each other, the magnitude is going to be root 3 times. So 1 is to 1 is to root 3. Okay, so as simple as that. Okay, and we move to the last two problems where we see that we have a three-phase circuit. Okay, and then we have three inductors connected in delta, and in between them we have three capacitors connected in star. Okay, and so let's see the balanced three phase. Okay, so the supply voltage is balanced. The circuit shown below, the value of inductance C is 10 millihenry. Okay, so that's given. The capacitance is given as equal to 10 millihenry. The value of the capacitance C, sorry, the inductance is given as 10 millihenry. The value of the capacitance C for which all the line currents are 0. So what does it mean? Together, that is the current and that the inductor and the capacitor should give rise to what is called as an open circuit. Okay, and that's possible only if you can have a similar kind of circuit. So you can go for either a star equivalent or a delta equivalent. Okay, so what has been done is that there is a star in between the circuit. Okay, so all options are okay. Okay, so here since we have a star of capacitors in between, you can always find out the equivalent of the star when you convert it into a delta. Okay, so when you are converting into a delta, when you are having a capacitor assembly, so it's going to be one third the value, or one impedance multiplied by the other impedance. So it's impedance value, so it's going to be 1 by j omega c. Okay, so 1 by omega c into 1 by omega c divided by 1 by omega c plus 1 by omega c plus 1 by omega c, because the capacitors are all of equal value. Okay, so now we see that, so and then they should be equal. So once they are equal, then since they are parallel with respect to each other, so in each of these branches, then what happens is that they provide an open circuit. Okay, because yeah, we have z1 into z2 divided by z1 plus z2. So one has j, the other has minus j, and they have equal values, and so you have 0 on the denominator or an open circuit. So they don't. So the entire circuit will not permit any current to flow. This is the concept here. So we see that since j omega L is the same as equal to minus j by omega c by 3, because we have, okay, so you just so now you substitute for all the values, and you see that the capacitance is the same as the capacitance, because omega is equal to 2 pi f, and f is equal to 50 hertz, so 340. So you can see that the capacitor value is equal to 3.0. Okay, for the now coming to the last problem here, we have a set, we have three-phase supply again, 100 ohms, J50 and minus J50 in a star connection. They are all individual, they are all different, and so we don't have a balanced situation here. But the question is that a set of 3 equal resistors, each of value Rx, okay, connected in star across R by B of given figure, consumes the same power as the unbalanced delta connected load shown. Okay, the value of Rx. Okay, so the problem is a little different. It has 2 main concepts. One is that of the 3 quantities in the circuit, only the resistor 100 ohms absorbs power. Okay, so how much power does it absorb? And that power is now going to be shared by an equivalent circuit wherein we have only equal resistors connected in star. Okay, so this is the idea. So what's the total power? That's what we have got to find out. Okay, so power consumed by 100 ohm resistor is equal to what? Okay, so there's a 400 volt across it. Okay, so 400 square divided by 100, which is equal to 1600 watt. I suppose this is understood very well. Okay, it's very simple, because the 100 ohms resistor, which is the only consumer of power, has 400 volts across it, as is given in the figure. So it's 400 square divided by, okay, just like a single phase circuit, but of course it's a 3-phase circuit, because the other 2 components don't consume any power. So 1600 watt. Okay, so now each of these resistors need to consume the same power. Okay, so we consume 1/3 the power. Okay, and so that's what is given here. So Rx is the same as equal to, now they are connected in star, so the voltage is now going to be 400 by root 3 across them. Okay, so and so 3 into 400 by root 3 whole square divided by 1600 by 3, because 1600 by 3. Okay, so 1600 is on the denominator, 3. Okay, so Rx is the same as equal to 100 ohms. Okay, so as simple as that, and that concludes our first session in 3-phase circuit. Okay, so thank you.